When you think of stars, you might picture the sun, a big ball of gas, warm and friendly at least from 150 million kilometers away. But not all stars live such a stable, gentle life. Some go through dramatic endings, collapsing under their own gravity, exploding in supernovae and leaving behind objects so dense and extreme that they almost sound like science fiction. One of the most fascinating of these remnants is the neutron star. Neutron stars are the ultimate paradox, tiny yet massive, dead yet active. Invisible to the naked eye, yet among the brightest sources of radiation in the cosmos. They pack the mass of a star into a sphere the size of a city, and if you tried to bring a teaspoon of neutron star matter to Earth, it would weigh more than Mount Everest. Imagine trying to stir your morning coffee with that. Suddenly your spoon bends like a cartoon gag, and you regret everything. In this essay, we will embark on a journey across 10,000 words to explore these cosmic oddballs. We'll learn how they form, what they're made of, why they spin so fast, and how scientists on Earth detect them despite their tiny size and vast distance. We'll meet their celebrity cousins, the pulsars and magnetarzans, see how they tie into the biggest cosmic dramas like black hole mergers, gravitational waves, and the origin of gold and platinum. So buckle up, because neutron stars are dense not just in physics, but also in the stories they tell about our universe. The life and death of massive stars. To understand neutron stars, we have to start with their parents, massive stars. Ordinary stars like our sun live long, stable lives because they strike a delicate balance. In their cores, nuclear fusion pushes outward, producing light and heat. At the same time, gravity pulls inward, trying to collapse the star. This balance, known as hydrostatic equilibrium, keeps stars happy and shining for billions of years. But what happens when the star is massive, say, 8 to 25 times the mass of the sun? Then the life story gets more dramatic. The fusion cycle. Stars are like cosmic forges. First, they fuse hydrogen into helium. When hydrogen runs out, they fuse helium into carbon, then carbon into oxygen, neon, silicon, and eventually iron. Each stage is like moving up to a heavier element on the periodic table. The problem comes with iron. Iron is the cosmic party pooper of fusion. Fusing iron doesn't release energy, it consumes it. So once the star's core fills with iron, the outward pressure from fusion stops. Gravity, which has been patiently waiting for its chance, says, "Finally, my time to shine, or rather, to crush." Core collapse and supernova. The core collapses catastrophically, shrinking in a fraction of a second. Protons and electrons are squeezed together, forming neutrons and releasing a flood of neutrinos. The outer layers of the star crash inward, bounce off the now super-dense core, and boom, a supernova explosion. This explosion briefly outshines entire galaxies and blasts heavy elements into space, so yes, the gold in your jewelry and the iron in your blood likely came from one of these ancient explosions. What's left behind after the explosion? Two things can remain, depending on the star's mass. If the core is below about 3 solar masses, gives a neutron star. If the core is heavier, gives gravity wins entirely, and it collapses into a black hole. And so, the neutron star is born not in peace, but in violence, like a phoenix rising from nuclear chaos. What exactly is a neutron star? At first glance, calling them neutron stars seems like lazy branding, but it's actually very accurate. These stars are made almost entirely of neutrons, the neutral particles found in atomic nuclei. Size and mass. Radius, about 10 to 20 kilometers. That's the size of a city like Toronto or Los Angeles. Mass, 1.4 to 2.5 times the mass of the sun. So yes, you could fit all of Manhattan into a neutron star, but it would weigh more than the sun. Parking would be impossible. Density. This is where things get insane. A neutron star's density is around 10 grams per cubic centimeter. Translation: 1 sugar cube-sized piece of neutron star matter would weigh 1 billion tons. That's heavier than every car on Earth combined. If you dropped it on Earth ignoring that it would sink through the crust like butter, it would tunnel straight through the planet and keep going until it popped out the other side like the world's most destructive yo-yo. Gravity at the surface of a neutron star is about 10 times Earth's gravity. If you weighed 70 kilograms here, you'd weigh about 14 trillion kilograms there. No diet plan could help you. Even light struggles to escape. Neutron stars bend spacetime so much that they act like cosmic funhouse mirrors, distorting the view of background stars. The physics holding them together. You might wonder, how can something that dense not just collapse into a black hole? Neutron degeneracy pressure. Enter quantum mechanics. The same weird rules that explain why electrons orbit atoms also prevent matter from being squeezed infinitely. In neutron stars, neutron degeneracy pressure resists further collapse. It works like this: neutrons, like electrons, are fermions. Fermions hate being in the same state. It's like trying to cram 50 introverts into one elevator. They'll resist with every awkward shuffle and cough they've got. In physics, this no two fermions in the same state rule is called the Pauli exclusion principle. This principle creates an outward pressure that balances gravity. For neutron stars, this degeneracy pressure, plus some help from nuclear forces, is enough to hold the star up unless it gets to massive, in which case, boom, black hole. The Tove limit. This upper mass limit is called the Tolman-Oppenheimer-Volkoff Tove limit. It's roughly 2 to 3 solar masses. If a neutron star core exceeds this, no force in the universe can stop collapse into a black hole. So, neutron stars are like cosmic tightrope walkers, perfectly balanced between stability and collapse. Types of neutron stars. Not all neutron stars are the same. Like celebrities, they reinvent themselves under different stage names. Pulsars, discovered in 1967 by Jocelyn Bell Burnell. Pulsars are neutron stars that rotate extremely fast and beam radiation like cosmic lighthouses. Some spin hundreds of times per second. Their beams sweep past Earth, appearing as pulses of radio waves or light. Astronomers first thought they had found aliens. They even nicknamed the first pulsar LGM-1 for Little Green Men. Spoiler, no aliens, just crazy physics. Magnetars, these are neutron stars with magnetic fields a quadrillion times stronger than Earth's. If you brought a magnetar within 1,000 kilometers of Earth, it would erase every credit card and fry every laptop instantly. Suddenly, your tech addiction would be cured. Magnetars sometimes release giant flares, bursts of gamma rays that can outshine all other stars in the galaxy for a brief moment. Binary neutron stars. When two neutron stars orbit each other, things get spicy. Their dance loses energy through gravitational waves, ripples in spacetime, causing them to spiral inward until they collide. These collisions create kilinovae, producing heavy elements like gold and platinum. So yes, every wedding ring might owe its existence to two neutron stars smashing together billions of years ago. Romantic, isn't it? Observing neutron stars. Neutron stars are small, dark, and far away. So how do we detect them? Radio waves and pulsars. Radio telescopes pick up the pulses of rotating neutron stars. Pulsars are so precise they rival atomic clocks. In fact, astronomers use pulsars to test Einstein's relativity and may one day use them for galactic GPS. X-rays and gamma rays. Accreting neutron stars, those in binary systems, steal material from a companion star. This matter heats up and shines in X-rays before crashing onto the neutron star surface. Telescopes like Chandra and XM Newton spot these cosmic vampires. Gravitational waves. In 2017, detectors LIGO and Virgo captured gravitational waves from two merging neutron stars. This event, GW170817, was a jackpot. Scientists observed both gravitational waves and light, ushering in the era of multi-messenger astronomy. Neutron stars versus black holes versus white dwarfs. Think of stellar remnants as a cosmic family. White dwarfs, lightweight cousins, supported by electron degeneracy. Max mass, approximately 1 point for solar masses. Neutron stars, middleweight champions supported by neutron degeneracy. Max mass, approximately 3 solar masses, black holes, heavyweight monsters, no limit. If stars were boxes, white dwarfs would be featherweights, neutron stars the heavyweights, and black holes. Well, they'd just eat the ring, the referee, and the audience. Open mysteries. Despite decades of study, neutron stars still keep secrets. What is the true equation of state of matter at such densities? Do exotic particles like quark matter or hyperons exist inside them? How strong can a neutron star's magnetic field really get? Could strange stars made of pure quark matter exist? These questions keep astrophysicists up at night, and not just because they're staring at telescope data at 3 a.m. Neutron stars in pop culture and humor. Neutron stars occasionally pop up in science fiction, sometimes realistically, sometimes not so much. Hollywood likes to throw them in as exotic backdrops without explaining the messy physics. But imagine this, a neutron star as a tourist destination. Come visit Neutron Star National Park. Warning: gravity will crush you instantly. Souvenirs available in the afterlife. Or consider a neutron star dating app profile. Height: 20 kilometers. Weight: 2 suns. Hobbies: spinning rapidly, beaming radiation, warping spacetime. Looking for another neutron star to merge with and create precious metals. Neutron stars are cosmic laboratories, testing grounds for physics we can't replicate on Earth. They challenge our understanding of matter, gravity, and the universe itself. From their violent births in supernovae, to their incredible densities, to their dazzling roles as pulsars, magnetars, and kilonova progenitors, neutron stars are among the most fascinating objects in astronomy. They remind us that the universe is stranger, denser, and more wonderful than our everyday experience suggests. So next time you look up at the night sky, remember, some of those stars will one day collapse, explode, and leave behind these tiny, terrifying, and beautiful remnants. Without them, we wouldn't have gold, platinum, or even iron in our blood. In a way, we are all children of neutron stars, just not quite as dense.
And that, my friends, is the incredible, mind-bending, sometimes terrifying world of neutron stars. From their explosive births in supernova, to their strange lives as pulsars and magnetars, to their dramatic collisions that literally sprinkle gold and platinum across the universe, these stellar remnants are proof that reality is often stranger than science fiction. Think about it. A star the size of our sun collapses down into something no bigger than a city, spinning hundreds of times per second, blasting out radiation like a lighthouse from hell. A teaspoon of its matter could outweigh Mount Everest. And yet, these bizarre objects are not just curiosities, they're central to the cosmic story. Without neutron stars and their explosive origins, Earth itself wouldn't exist as we know it. The iron in your blood, forged in a massive star's collapse. The gold on your jewelry, probably born from 2 neutron stars smashing together in a kilonova billions of years ago. In a sense, every one of us is carrying a tiny bit of neutron star history inside our bodies. Neutron stars also remind us that the universe is a giant physics lab, one we can't replicate on Earth. They test the limits of quantum mechanics, nuclear physics, and Einstein's relativity all at once. Every observation, whether it's a pulsar ticking like the most precise clock in existence or gravitational waves rippling from a distant collision, gives us clues about the ultimate laws of nature. They're like cosmic exam papers that the universe hands us, and so far, we're still scribbling down answers, hoping we're getting at least partial credit. But beyond the science, neutron stars also spark our imagination. They're the kind of objects that make you step back and say, wow, the universe is wild. They stretch our sense of scale, they defy our everyday intuition, and they show us how small but also how connected we are to the cosmos. So next time you look up at the night sky, remember, hidden among those twinkling points of light are stars that will one day collapse into neutron stars, spin at dizzying speeds, maybe merge with a partner, and in the process, shape the very building blocks of life and civilization. If you enjoyed this journey into the strangest stars in the universe, don't forget to hit that like button, share this video with your fellow stargazers, and subscribe for more deep dives into the mysteries of space. Drop your questions or favorite neutron star facts in the comments. I'd love to hear your thoughts. Until next time, keep looking up, keep wondering, and remember, compared to a neutron star, none of us are really that dense.